感谢两位嘉宾的精彩的演讲。Thanks for your speech. 大家现场有没有想跟两位嘉宾进行一个互动的 ？Is there anything you want to share with Mr. Hackett and Mr. Urao? Okay, thank you. Thank you. 下面有请英特尔软件工程师程迎新先生，他的主题是 Ceph 集群的瓶颈定位及分析，大家欢迎。Let's invite Mr. Cheng Yingxin, Intel software engineer, to give us a speech.
Hi everyone, my name is Chen Yingxin. I'm a software engineer from Intel. I'm currently working on the performance analysis of Ceph. So today's topic is Pinpoint Ceph bottleneck out of cluster behavior mists. The motivation is, of course, the bottleneck is a very important part in performance analysis, and it is a very difficult task to identify bottlenecks in a very complicated system like Ceph. And I want to share there's a way to do it instinctively and very fast. And I also want to share the important use cases of distributed tracing. Okay, so let's start. And you can also reach me personally or through this email, and we also have a demo outside in the Intel booth. You can ask me then. So I want to reason the entire idea by reasoning three fundamental questions. Why performance matters, what is performance, and how to improve it. They will help understand the ideas about how to better collect better performance data and how to represent performance from the data collected and how to do the following analysis and improvements. So first, why performance matters. Of course, we don't want users feel the Ceph system, very laggy and unresponsive. So it means that if we do not have enough time to monitor all the activities inside the Ceph, and even we don't have enough time to analyze all the latencies in the user requests, but we should not overlook all the costs that is directly related to the request response process, because any of them could be the bottleneck and be the culprit of the bad user experience. So using existing tools, I think it is very tedious and time-consuming to collect all the latencies from every corner of Ceph components. But I think the better way is to not collect the latencies manually, but to use a distributed tracing to rebuild the history of requests and start from the responding point to find a critical path to the request being sent, and collect the responding costs on that critical path. And we built up a prototype to do this. This is an example of a Rails write requests across one client and 3 OSDs in that cluster, and it is built based on pure happens before relationship between events. And the costs between these events are either in-thread execution or cross-thread and even cross-host relationships. The cost of in-thread executions and the cost between threads and processes. And we can start from the responding point. There is one way back to the request being sent, because of the definition of the critical path is the longest execution path. And because the events are consecutive, their costs are not overlap. So it brings us a very big advantage to show the performance of concurrent requests. And in order to explain this, I need to first explain what is actually performance. The performance is basically a two-dimensional concept, latency and the throughput. And it is very easy to understand if we want to transport a group of people. If you use planes, it is very fast, so it has good latency, but it can only take a limited number of people, so it the throughput is not very good. But on the contrary, if we use trains, it can take a huge amount of people, so the throughput is good, but the latency is not, because this train is relatively slow. And we usually accustomed to latency-only analysis, like the Ceph curve counters, or collect metrics of latencies. And or we usually are accustomed to measure requests individually, use OSD OP trackers, or using the Ceph bulking tracing, that is the distributed tracing solution in Ceph. I think if we want to understand what the performance in the real system correctly, we need to focus on the performance of concurrent requests. And we also need a new visualization for both request throughput and the latency. And here the throughput is about the number of requests per second, but not the payload of these requests, like how many bytes they write in a second. And then, for example, to visualize a function in a very complicated system like Ceph, we can first draw two lines to represent the throughput that goes inside this function and the throughput goes out of this function. And the more steep the line is, means the better throughput. And the distance between these two lines represents the latency of that function. So if we improve this function to have better throughput, we'll see that the line of the out throughput will be better, will be more steep. And if we improve the same function with better latency, you can see the result, the distance between two lines become reduced. And in the ideal situation, if it has better latency and better throughput, we can see two lines close to each other, and we can only see one line. And so, how to represent the performance of concurrent requests? Now we have one critical path per request, and that is with consecutive costs. Then we can stack the critical paths together and aggregate the costs by its logical steps. And so we can represent the latency and the throughput of individual steps. And because the out throughput of the previous steps equals to the in throughput of the following steps, because the steps are consecutive. And so we can see the representation of these steps can fit together, and they together shows the performance of concurrent requests. And the more important of that is that we can show the performance behavior that is very hard for existing tools. For example, if we generate write inputs from FIO and setting the IO depth equals to 32, and we can see clear from the second graph that the FIO will wait until the previous request being finished until it sends another the later group of 32 concurrent requests. And next, how to understand the bottleneck in that graph. And the bottleneck is also I think it is also a two-dimensional concept. The latencies of different steps are not necessarily dependent, because if we transport a group of people, first to take planes and the next to take trains, the speed of the plane and the train are independent to each other. but the throughputs are not, because the low throughput of the plane will limit the throughput of the train. So it also means that the lowest throughput in the entire procedure will usually define the throughput of entire procedure. And it also, the worst case is that the lowest performance point will cause the requests being weighed before this point, this lowest throughput point, and it causes wait latencies in those requests. And most of the case, it becomes the bottleneck of the entire system. And we can very clearly see this pattern in that representation of performance. Okay, now performance can be identified relatively easily, and next is how to improve the performance. The very short answer is to identify the root causes of the bottleneck and then to resolve them and improve the performance. But the reality is much longer because there are many kinds of factors that can impact the performance. For example, in 3 categories: physically, the system, the cluster configuration, or how we deploy the cluster, or which hardware we use in that cluster will affect the performance. And secondly, logically, the parameters we choose in functions and the different algorithm we choose and the whole architecture of the entire software can have impact to performance. And other workload at the same time, whether it is in the system or it's in Ceph, will impact the performance. So there are almost infinite combination of these factors, and I think it is bad to do optimization in blindness. Because we have identified the bottleneck and also identified the related costs of that bottleneck, and we also related each cost with its physical location, like where the host it is, where the component and process, even the thread where it is, and the logical location, like where the code it is, which code is related, and which step is in the workflow, and also attach the runtime context of requests, like which request ID and what is the write length, what is offset, and what type of operation it is. And because it is associated, we can index those costs and do incremental analysis. It means to use controlled variables or orthogonal methods to see the impact of different factors and find what to do to improve the performance, and then verify these solutions to see if it is actually better. And the incremental analysis means the incremental analysis means there needs to be an interactive front end to do the data-driven analysis. And so we need first to understand how those factors impact the system performance by using custom statistics and custom visualizations to understand them, and then to dig deeper by filtering out the related costs or a subset of requests to have a deeper analysis. Okay, so that's all of the entire idea about how to identify bottleneck in the Ceph system and to do the following optimizations. And we leverage the distributed tracing to collect the critical paths on the user requests, and then we developed a visualization technique to represent the performance straightforwardly. And we developed an interactive front end to do the incremental analysis. And here is the example. We built up a prototype to track the RBD image writes inside the Ceph cluster. And there are 3 requests related. On the RBD layer, there are image write requests that internally represents the write requests in that image. And this request will trigger object requests to write the data into the objects in that image. And then at Rados level, the object request triggers object write operations to persist the data across the entire cluster. And we deployed a 3 VM environment and use FIO to generate write inputs and collect the tracings during the experiment. And then in the interactive analysis front end, we load the data, we load the tracing result into a variable called data, and pass that data into the 3 types of requests. Of course, there are many other requests in the Ceph system, but we think that these 3 is the most important. And this interactive front end is built based on Python Jupyter. It is a very famous open sourced web application to do the data-driven analysis. And then we can visualize the performance of these 3 requests. We can see on the top the image, on top level, the image write requests. We can see very clearly that the bottleneck is at the step the image context write X operation to the operation is completed, and we can choose to highlight this step in that graph, and I choose the purple color. So we can see that all the codes are related to this step, and this step means the write X operation in fact triggers the object request in the next layer, and we also can directly find out that the bottleneck is at the OMAP operation, object map operations, and the AIO operate operations. And these two operations actually triggers the object write operations at Rados level, and we also identified the bottleneck as the 3 steps, and they represent the queue operations in OSD queue operations and the actual disk writes in the object store. So actually the whole bottleneck is limited to, at this environment, is related to the queue operation and the writes in the object store. And then we do deeper analysis. Firstly, to filter out for example, the OSD queue operations by their step name, and then we find if these costs are related to the physical location. So we represent the distribution by where the host it happens, and we found that the median number are similar, so that it has less impact by the host. And then we try to find out if it is related to the logical location for the happen order in the logical workflow, and we found that the first occurrence of the in-queue operation in OSD has a much larger median number, and it means that this latency means that the following do OP operation in primary OSD doesn't have good performance by using this interactive analysis. And then we start to find out the root causes of why this in-queue operation becomes so slow. And we found out 3 related configurations. The first is the number of page groups of the pool. And the second is the number of threads per OSD shard. And the third is the number of shards in that OSD. And we found that very clearly that if we increase the number of shards, the bottleneck of the in-cure operation will be disappeared. And we can, so in this environment, we can do optimization to increase the shard numbers. And then we found that all the costs are concentrated in the right operation in object store. Then we can find out better configurations in object store, or to try to find a better disks like SSD. And the interactive analysis actually can do more than that. For example, to represent all kinds of distributions, or to find out the longest or the most complex requests and visualize those requests, and or we can represent the message heat map between hosts of the entire cluster. And at higher level, because we attach the runtime context with this request, we can analysis if the write in OSDs are balanced across the entire cluster, or by comparing the behavior of image write requests in RBD and the object requests in RBD to find out if the RBD cache is valid or it works good. And if we can combine it with resource monitoring tools like Zabbix, we can find out the specific logic that consumes excessive resources. Okay, that's all of this presentation, and thank you for listening. Thank you.